Hi everyone, this is Abhinav and today we'll be discussing the 23rd problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. Let's begin. We'll move on to our CP-31 sheet and we can see that the 1500 rating mark is checked. Let's move on to the 23rd problem um, which is Lunar New Year and a Wonder. Okay, so let's read the problem statement. The park can be represented as a connected graph with n nodes and m bidirectional edges. Initially, Bob is at the node 1 and he records 1 on his notebook. Okay, so you are given a connected graph with bidirectional edges and nodes m edges, and Bob is initially at node 1. He records 1 in his notebook. He can wander from one node to another through those bidirectional edges. Whenever he visits a node not recorded on his notebook, he records it. Okay, so he can go through any of the nodes. He can just wander through any of the nodes, and the first time when he visits a node, he records it in his notebook. If he visits it again while wandering, he doesn't record it again. Okay, so after he visits all nodes at least once, thus he would obtain a final permutation a1 to an. Okay, so he would finally obtain a permutation of these n nodes according to the first time when he visits a node, he is noting it down in his notebook. Now, wandering is boring thing, but solving problems is fascinating. Bob wants to know the lexicographically smallest sequence of nodes he can record while wandering. Bob thinks this problem is trivial and he wants you to solve it. Okay, so basically we need to find the lexicographically smallest sequence of nodes that we can obtain through this wandering process. Okay, and I hope you know what lexicographical order is. So X is lexicographically smaller than Y only if the first position where x and y differ, x is smaller, x has a smaller element than its corresponding y. Basically, the first time when the two sequences differ, whichever sequence has a smaller element, that would be lexicographically small. Okay, the whatever is there ahead of that, that doesn't matter. So always in lexicographical type of problems, you have to like think a bit greedily starting from the start. The first time where they differ, after that it doesn't matter, so you have to like think greatly. So okay, let's look at the example discuss to understand more clearly. So you are given this graph where this is n, this is m. So your n is equal to 3. That means the graph has three nodes, 1, 2, and 3. Okay, and these are the edges. From 1 to 2, there is a bidirectional edge from 1 to 2, and from 1 to 3 there is a bidirectional edge from 1 to 3. Okay, so this is the graph given to us. It is always a connected bidirected graph. Okay, now for this graph you need to find the lexicographically smallest sequence you can obtain by wandering. So what is happening is initially Bob is at, let's say initially Bob is at node 1. Okay, so Bob is at node 1, he would note down 1 in his node. Okay, then Bob has choice. When he is at 1, he can either move to this node 2, okay, or he can move to this node 3. These are the only two choices. So in order to obtain lexicographically smallest, what we would do, we would move to node 2, and when he moves to node 2, this also gets visited and it gets written in his node. Okay, then from 2, only option to him is get back to 1. Okay, so he would get back to 1, but this 1 is already noted, so he won't note it again. Okay, now again he is at 1, then he can just roam around here. It doesn't matter, it would not get counted in his notebook. Whenever he visits this 3, okay, whenever he visits this 3 gets noted down in his notebook. So the final permutation that he obtains is 1, 2, 3. Okay, another way available to him was if he starts with node 1, then he can probably move to node 3 next from here. Okay, and then come back to 1 and then move to node 2. That way after 1 he would note down 3 and then 2. So this was another possible permutation, but among these two permutation, which is the lexicographically smallest one? This one is lexicographically smaller, because at this second index this is 2, this is 3. So The lexicographically smallest permutation we can obtain here is 1, 2, 3. This was our answer for the first test case 1, 2, 3. Okay, so I hope you would have got what the problem is trying to say. Let's look at the solution. Before that, let's analyze the time complexity by looking at the constraints to know which time complexities would be optimal for the problem. So n and m are given up till 10 to the power 5. So n and m both are up till 10 to the power 5. So what time complexities would be fine for this problem? Both n and m are 10 to the power 5, so something like order of n or even n plus m, these would be fine. But if you go to something like order of n into m, something like that, this time complexity won't be fine. So you have to solve the problem in some linear time, or you can even have something like extra log n log m, something like those things, can extra log factors can come in there. So these we can say are our expected time complexity in which we need to solve the problem. Okay, so once you know this, now let's try to find a solution to this problem in some linear time. Okay, so what you are given is you are given a graph. Okay, so that can be some any random graph. Let's say you have a 1 here, 2 here, 3, 6. Okay, so from here, let's say you can go to 3, 4, or let's say here you have 5. Mm, let's say you have some random graph like this. Okay, now for this particular graph, what you need to find out, you would start at this node 1. Okay, and once you are at this node 1, this is visited and already noted down in your node. Okay, you would always have this one noted down initially. Okay, after that, it's on you where you have to move in order to get the lexicographically smallest sequence. Okay, so once you are at 1, next choice for you is you can move to any of the adjacent nodes. So you can either move to 2, 5, or 6. All of the three are not visited, so wherever you move, that would get noted down in your notebook next. So as I told you, you have to find the lexicographically smallest sequence. So in order to minimize lexicographically, you have always have to think greedily. So the next value that should come, if you have a choice between 2, 5, and 6, if you are choosing 5 and not going for the smallest one, then whatever comes after that, that doesn't matter. If you had chosen 2, that would have been lexicographically smaller than whatever is. So if you have a sequence starting with 1, 2 and a sequence starting with 1, 5, among them this would always be smaller. After that, whatever you take, that doesn't matter. So it's always greedily the best choice to take 2 next. That I hope is clear. So from here, your next optimal choice would obviously be 2, because among these three, 2 is the smallest one. Okay, now you went to 2. Okay, you are at node number 2. You have noted down 2 here. Now, when you are at node 2, what is the next number that can come in your sequence? So here you have, with adjacent to 2, you have three nodes, 4, 3, and 1. So either you can move to 4, then you would get 4 noted down here, or you can move to 3, then you would have 3 noted down here, or you can move to 1, then you won't have anything else noted down here. Then so you can, from 2 you can move to 1, and then from 1 you can again move to either 5 or 6. So basically, if you go back to 1 and then move to 5, then you would have a 5 noted down here next. Or you can move back to 1 and move to 6, and you can have a 6 noted down. So basically, the third number that is coming in the sequence, what are the possible options for that is from the values that are adjacent to 2 as well as the values that are adjacent to 1. You can also pick those values as next by moving back to 1 and then moving to them. So among all these four values which you can see, which is those values adjacent to 2 and those values adjacent to 1. So all these four are your next available options. Among them, which is the smallest one? 3 is the smallest. So you would pick 3 by using the greedy approach, and you would move to this 3. So, okay, you would now move to this 3 and note down 3 in your notebook. Okay, now if you look, what is the next choice for the next number? So from 3, either you can move any of the adjacent edges like 5 or 7, or you can go back to 2. If you go back to 2, that won't get noted down in your notebook because it is already noted. So either you can move to 5 or 7 and note it down. That would be the fourth number that is coming in your notebook. Or you can go back to 2 and then maybe go to 4, one any adjacent of 2. So 4 would be the next that can be noted down. Or from 3 you can go back to 2 and again go back to 1, and then you may go to 6 maybe. Okay, so from 3 you could have directly gone to 5, or you could go in through this way also. By both these ways you would have 5 noted down next. Or you can move here and note down 6, move here and note down 4 also. So what are the available options for the next number is all those adjacent to 3, which are 7 and 5, all those adjacent to 2, which is 4, all those adjacent to 1, which is 6. So you have these four available options. So which one would you choose among the four? 4 is the smallest one. So you would note down 4 here by moving like this. So from 3 you would go back to 2, you would go back to 2, and then from 2 you would go to 4. So you would be at 4, and this 4 would become visited and get noted down here. Okay, so now this is done. Now what is the next choice available to you? From 4 the only adjacent is 2, so you would have to move back to 2. Okay, but this won't get noted down in a note. From 2 again, all these adjacent are already noted, so you can just roam around here or go back to 3, and then from 3 you can go to 5 or 7, or go back to 1 and you can go to 5 or 6 from there. So the next available options are all those adjacent to the currently visited nodes. So through this like dry run, you would have got the logic. What we need to do is basically at any point of time, the visited nodes would form a connected graph always. Okay, whenever you are visiting some nodes, they would obviously the visited nodes would obviously be connected, then only you are able to visit all of them. If there is some one node in the middle which is not visited and all those around are visited, that is never possible, because you would have to cross through that node in order to visit. So always the nodes which are visited once would form a connected graph in itself, and from that connected graph, all those nodes adjacent to the nodes present in the connected graph, they would be the next available choice for you, and among them you are always choosing the lexicographically smallest. So here this is the connected graph to you, and among them these are the nodes adjacent to that connected graph, and among them you would choose the one which is smallest lexicographically. Here it was 5, so we note down 5, and you would say that this 5 gets included in your connected graph. So your connected graph gets expanded like this. Again, from this connected graph, the only adjacent nodes are 6 and 7. So you would note down 6 and say this also gets included in our connected graph. This connected graph has got expanded. Now the adjacents are 7 and 8. So among 7 and 8, the smallest is 7. So you can note down 7 and say that this is your connected graph now. Okay, and then only 8 is left. You can note down 8 and say all of the nodes are visited, and then you are done. So this way you can get the lexicographically smallest sequence. Okay, I hope you got the intuition that how it is working and why this approach is correct. You would have like understood, got a kind of a proof in your mind that by this type of greedy approach, you would always get the lexicographically smallest. So basically start with node 1, whatever nodes are adjacent to them, among them whichever is lexicographically smallest, include them in the your group of connected graphs, and all those nodes which are adjacent to them, include them in the available choices. Okay, so how and then keep on expanding like that. So your connected graph or the list of selected nodes is getting expanded, and all those adjacent to them, that list is getting updated, and among them you are choosing the smallest one. So how do you do this whole process in some linear time or in optimal time? If you are just trying the brute force approach, like you start with node 1, and among the adjacent you pick the smallest. Then once you have like a connected graph of, maybe let's say some connected graph of some selected nodes, like when you are, let's say, at this state, you have some connected graph, you want to check which are the available options for that. If you are doing that for all those currently visited nodes, if you are going to all the adjacent edges of all those nodes, then it may take an overall order of n square time, because every time this whole may become an order of n size, and if you are going to all the adjacent edges, there may be order of m edges. So this overall may go n into m if you are doing in a brute force way. But in order to do it optimally, what you can do is you can maintain that through a priority queue. So in a priority queue, you can keep hold of all those options which are currently available to be picked next. What I mean by that is, let's say, okay, let's say you start with node number, so you would always start with node number 1. Then what you can do is, in a priority queue, you can store all the nodes adjacent to node number 1. So all those nodes adjacent to that is 2, 5, 6. Okay, so this is stored in a priority queue. Okay, then pick the smallest element from the priority queue, visit that. Okay, so pick the smallest element and visit that. Okay, then you will update. You had 1 written, then you will write 2, and once you visit this node number 2, insert all the nodes adjacent to node number 2 which are unvisited currently into the priority queue. So you would insert this 4 and 3 into your priority queue. Okay, so your priority queue get updated with 3, 4, 5, 6. Okay, your priority queue is now updated with all those adjacent nodes. Then whatever is the smallest in this priority queue, which is 3, visit this 3, note it down, and then all those nodes adjacent to this node 3, put them into a priority queue. So you'll put this 7 into your priority queue. Again, look at the current priority queue, whichever is the smallest value, pick this up, visit that, and insert all those nodes adjacent to this node. Okay, here there were no unvisited nodes adjacent to 4, so nothing got inserted in the priority queue. Then visit this 5. Okay, insert all the adjacent nodes, there's nothing adjacent to it. Visit this 6, insert all the adjacent nodes, so 8 gets inserted here, and then visit the 7, visit the 8. Okay, so this way you can do it. And while inserting into the priority queue, at max you'll insert n nodes into the priority queue and uh, take back n. So overall in n log n time, your algorithm would be working. Okay, so it is somewhat similar to a BFS, but using a priority queue. You can understand it like, in a BFS you use a normal queue, and whenever you visit a node you insert the adjacent nodes into it. But here, instead of using, because if you are using a queue, you are doing it like first come first serve basis, whichever is gets inserted first would come first from the queue. But here what you needed to do is visit those nodes first which were having lower value, in order to have the lowest lexicographically subsequence or the sequence. So you are using a priority queue in order to, whatever is the available options next, whichever has the smallest value, take that first. So it's same as a BFS using a priority queue. Okay, so I hope you got the logic for the problem, and through this diagram you would have understood what we are doing. If you want, we can just run a quick dry run on one of the given test case. Okay, so for this test case, we had n equal to 5 and m equal to 5. So we have 1, 2, 3, 4, 5 nodes. So 1 is connected to 4. So 1 is connected to 4. 3 is connected to 4. And 5 is connected to 4. Then 3 is connected to 2. And 1 is connected to 5. So this is the graph given to us. So if you run our algorithm to find the answer, you start with 1, note down 1 in your notebook, and then in your priority queue, what you would do is, in your priority queue you would maintain, okay, let's say we take the priority queue here. Okay, you note 1 in your notebook, and in your priority queue you insert all those adjacent to 1. So 4 and 5 got inserted in your priority queue. Okay, take out the minimum. If you take out 4, so the next available option was 4 only. So if you visit 4, then insert all those adjacent to 4. So 3 gets inserted in our priority queue. Okay, 4 got removed and 3 got inserted. Your priority queue is updated. Among them, let's pick the 3. Okay, so note down in your notebook. Insert this 2 in your priority queue. So this 2 got inserted in your priority queue. Okay, next smallest is 2. So visit this 2. Okay, and only thing remaining in your priority queue is 5. So visit this 5. Okay, so the sequence that you obtained was 1, 4, 3, 2, 5. So 1, 4, 3, 2, 5 you can see. Okay, so I hope you would have got the algorithm what you need to do. Let's quickly look at the code for it. Okay, so here we are taking the input n, m, and in an adjacency list I am storing the graph. Okay, so for the m edges, u dot pushback v dot pushback u. I hope you know how we store a graph in an adjacency list. So I have done that. This was for the input part. Okay, once input is done, then we have to run an algorithm like a BFS but using a priority queue. So we are taking a priority queue defined as greater int, so that the top of the priority queue is the smallest value and it's increasing. So we have defined this priority queue, and we are taking a visited array to mark the values which are visited. Okay, and we are taking an answer vector. So in that we'll push our sequence. Okay, so initially we start with pushing 1 into our priority queue and marking 1 as visited. Okay, then one by one we'll take out elements from the priority queue, push all its adjacent elements into the back into the priority queue, and like that. So while the priority queue is not empty, take out the top of the priority queue and pop it from the priority queue, push that into your answer array, and then all those elements adjacent to the node u, if they are not visited, push them into your priority queue and mark them as visited. Okay, once that is done, then whatever sequence you obtained in your answer, that is your final sequence. Okay, I hope the code was pretty simple and it is clear to you. If you analyze the time complexity from the code, then this input part was taking order of m time to input the m edges. Then all this push thing is taking a log n time. So while the priority queue is not empty, this is like a BFS thing where your this push operation is taking log n time, and this okay, top and pop are taking O of 1 time only, but this push thing is taking log n time, and at max you would push n elements into a priority queue. So overall it would take n log n time only. Okay, and this printing the answer takes order of n time. Okay, so overall you can say your time complexity is order of n log n, and your space complexity would be, you are using an adjacency list which would have a size of total size of n if you push or m if you push m elements. So order of m would be the size of the adjacency list, and a priority queue, it would have order of n number of elements that would be pushed at max. So you can say a space complexity is n plus m. Okay, so I hope the logic and the algorithm is clear to you. Okay, on the time complexity, you are going to all the elements, you are going to all the edges here. So this for loop in total would take an order of m times. So plus m would also be there. Okay, if you're considering the total number of times you are visiting, since you are visiting all the edges. So I should better write is n log n plus m for the number of edges that are visited. Okay, so I hope the time and space complexities are also clear to you, and the problem is clear. It was a pretty nice graph problem where you, instead of using a normal BFS, you had to use somewhat like a BFS algorithm but with a priority queue because of the lexicographical condition. Okay, so I hope you enjoyed the video. Thank you so much for tuning in.